recording, which is what you will have to use to solve for the one up here, 21b. Okay? So if we go through and attempt this, what we're going to do is look at our two reactions. We're looking at a change or a transfer of electrons, which means we're looking at a redox reaction. Okay? For it to be reduction, what has to happen? What was our definition for reduction? Gained electrons. What was our definition for oxidation? Loss of electrons. So let's pick one of those and see what changed. If we take a look at tin, what happened to it? It lost electrons, so it was oxidized. So if I'm going to color code, which I'm usually really bad at, but let's go ahead and see what happened. How many electrons did it lose? Okay, we lost 2 electrons. What happened with our iron? It had to gain electrons. So it was, yeah, go ahead. It was reduced. Okay, I know the English can be a bit dicey in sometimes. Okay, how many electrons were transferred? Just 1 electron. In the crossover method, what they're saying is take the electrons that were transferred and put that as a coefficient on the other species. So if we go through and take a look at our tin, the coefficient that should show in front of our tin needs to be the amount of electrons gained by our iron. How many electrons were gained by our iron? 1. So the coefficient we put in front of our tin is 1. What happened to our iron? Well, the coefficient that goes in front of that needs to be the number of electrons transferred from our tin, which means 2 and 2. Okay? In a simple example like this works out pretty well, and we don't have to stress too much with it. As we get to more advanced problems, particularly like 21b, it becomes a little bit more difficult to process, and we have to look at a couple different things as we go through and approach it. Okay? Let's verify that that was indeed actually balanced. If we check our atoms, do our atom counts balance? Yeah? How about our charge? What's the charge on the reactant side? There's a +2 plus. Why is it 6? There's 2 irons. We hope that that equals our +4 plus another 4, which gives us 8. Our charge does indeed balance. Okay, so we have balanced this equation. What I would argue is a little bit easier to at least visualize and see is to split it into the half reaction. So ultimately what the textbook has done is condensed a whole bunch of information into one tiny little section. If you make a mistake within that one tiny little section, it becomes virtually impossible to see that mistake because you've condensed it in a tiny little section. Okay? So what I would argue you should do is instead of looking at just that line, break it into the half reactions. Remember, to run a redox reaction, you have 2 parts. We have a reduction and an oxidation. So what we want to do is try our best to split our equation into those 2 separate reactions. So what are our half reactions in this case? What should we group together? Tin plus 2 goes to what? Does it go to iron plus 2? Why does tin plus 2 not go to iron? Are they the same element? Have we seen how we can change elements? No. So does it make sense to say tin plus 2 goes to iron plus 2? No. What does tin plus 2 convert to? Tin plus 4. So what we could do is write out our tin plus 2 going to tin plus 4. And we can also look at the other one, our iron plus 3 going to iron plus 2. Okay? We've already specified that these were reduction and oxidation reactions, but we could add that information now as well. Are these reactions balanced? How many irons do we have on each side of that equation? They're not balanced. Why? Our charges aren't balanced. So what we need to go through and do is balance our charge. Okay? What changed? Okay, to go from iron plus 3 to iron plus 2, what did we have to do? we had to gain electrons. So effectively, iron plus 2 reacted with an electron. I don't see that electron up there. What could I do? Let's add it. There's our electron. What charge is our electron? Negative. Does our charge balance now? What's the charge on our reactant side? Plus 2. Charge on our product side? Plus 2. Does our charge balance? Yeah. What happens in a reduction reaction? We gained electrons. So we put our electrons on our reactant side. They were part of the reaction. We had to add them into our structure. Okay? What happens when we look at our oxidation? Is our charge balanced there? Nope. What happened to our tin plus 2? It had to lose 2 electrons. Okay, what's our mathematical symbol for loss? Minus sign and negative. Okay, when we talked about our energy differences, our bond energies, remember I said there was a very important correlation with what that mathematical symbol meant. In an exothermic reaction, we had a loss of energy, a release of energy. Where did the energy term occur? Was that a reactant or a product? It was a product. Our loss, that mathematical symbol of a minus, is ultimately saying that whatever that species is, needs to show up on the product side. So in the course of running our oxidation reaction, we lost electrons. How many electrons did we lose? 2. The loss means it's a product. So what can I do? I will put my 2 electrons on the product side. What mathematical symbol should I put in there? Why plus and not the minus? It said loss. The loss was the interpretation of what side of the reaction it showed up on. When we look at a reaction, we will always use positive values. So when we see that mathematical symbol of a minus, that's just telling us that it's a product. Okay? So we'll put those 2 electrons on the product side. Did it make sense for us to do it that way? What's the overall charge now? Plus 2 on both sides of the equation. Our charge balances there. Okay? So what we've done is split this into the half reactions. We could now go through and add these 2 reactions up. So what we'll do is literally just take everything on the reactant side, add it up, and put it on a sum total for our reactants. We'll take everything on the product side, add it up, and we'll have a sum total on our products. I'm pretty sure I stepwise all of this. Okay? So when we go through and do that, okay, we'll end up with a full balanced reaction. You'll notice that when we added these 2 up, I don't see any electrons on the reactant side. Why not? There's no electrons on my reactant side. Kind of balances. What's happening is we're canceling out terms that show up on both sides of the equation. Okay? Our 1 electron that was a reactant in our reduction reaction cancels with 1 of the electrons that was a product. So we can eliminate those 2 from each other, and we end up with 1 electron left over as a product. Okay? Just like when we tried to simplify math terms, we can add and subtract on both sides of the equation. Okay? There's a big problem with this. We've generated an electron as a product. Okay? So in our overall equation, we kind of have an issue. What did we say was the issue with electrons? They are angry little buggers, cannot be stabilized on their own. Okay? They must be partnered with something. And the course of what we've got now drawn is we're saying we formed this angry little electron that can now run around and do things. Okay? That's not allowed to happen. The electrons must always be partnered with something. Okay? So that means in the addition of these 2 equations that we made a mistake. So we would have to go back through and evaluate our overall equations and say, how can I change how I add these 2 equations such that those electrons cancel out and I get 0 electrons produced and 0 electrons consumed. Okay? And that's where this becomes a little bit different. So we've got to go back through and make sure that we don't end up with that free electron, either as a product or as a reactant. Whoops. So what can we do? as I gave away the answer with the next tab. Okay, our electrons must completely cancel out, which means we have to find a common multiplier between them. So we have the same number of electrons on the reactant side as we have on the product. How can we do that? How can I make 2 equal to 1? I could divide by 2. So if I divide that second equation by 2, I don't react one tin atom. I react, whoops, come back here. I react a half of a tin atom. Can I react a half of a tin atom? No, that doesn't work. Okay, so I can't divide that 2 or divide that equation by 2 to get only 1 electron. Okay, because I need whole numbers in my balanced equation. So what do we do instead? We'll multiply our top equation by 2. And we're going to multiply everything within that equation by 2 because what we need is to consume 2 electrons. So I'm going to need 2 iron plus 3s to react so that I can get all of those electrons consumed. And that way I don't have anything left over. So what I'll do is multiply that entire equation by 2. Okay? I'm not going to change just the electron count. I have to distribute that 2 in through the iron atoms as well. Now when we look at our equation and we add these 2 up, what happens with our electrons? 2 on each side, they will cancel. Now when we add them up, we end up with our overall balanced equation. Okay? We get the exact same answer as the textbook did, and yes, we had to go through some more descriptions of what was happening at each of those stages. So what the textbook gave you was kind of said, here's how you get the answer with 0 explanation on why they use those individual numbers. Okay? So if you don't understand where they're getting these methods from, ultimately, if they fail, you don't know why it's failing. Okay? The reason it's working is because what we've done is split it into the half reactions and tried to balance out those electron counts. Okay? Questions about that? How much more tedious is this method over the textbook? It's a lot more steps. But it will hopefully allow you to see what's happening in each of those steps. One of the primary things you're responsible for is identifying reduction and oxidation. If we look at an overall equation, that doesn't jump out and stand out at you. But if you go through and split it into the half reactions and look at where your electrons are either consumed or produced, you might be able to identify your redox reactions or your reduction and oxidation a little bit easier. Yeah?
In this case, we're dealing with single elements in each case. If you're dealing with molecules, do you still pick out the individual elements when you're balancing out like this?
What you will do is pick out the individual, you'll have to pick out the molecule that's changing. And one of the things we'll have to hope for is that we don't see a bunch of other things changing in the same process. Okay? So one of the issues that you'll run into is what you've got up on the board. What is that one? 21B. Okay? How do we split this one up into half reactions? Okay, well, we could go through and say our lead sulfide, okay, and try and split that, except the problem, what happened to lead in the course of the reaction? Okay, I got partnered up with the oxygen. Well, actually, this does work. Lead is what oxidation state in lead sulfide? +2, our sulfur. Okay, we're looking at an ionic bond here. When we have an ionic bond, what happens to each of the atoms within it? They become charged. Do we know the oxidation state of sulfur as an ion? What is sulfur when we look at it in an ion? -2. How do you know it's -2? Because you look at the periodic table and you realize where sulfur is located. I know we talked about that such a long time ago. Okay? You have to keep going back and referencing it. That's why you should put the periodic table in front of you, so you constantly have access to that. So our sulfur is a -2, which means the charge on our lead necessarily has to be +2 to balance out that charge. We now know the charge on lead. How do we figure out its oxidation state? Okay, if you remember all the way back to our formula, We said it's the number of them times its oxidation state has to equal the charge. What did we say the charge was on lead? What's our oxidation state on lead? +2. Ends up being the same as the charge. Okay? Which is why it's easy to get those two confused. Sometimes they come out the same, sometimes they come out different. Okay? If we look to our product, what's the oxidation state of our lead here? Again, a bit tricky. We'd have to solve for it. We're looking at what type of bond between lead and oxygen. What is lead? What is oxygen? What type of bond do we have between a metal and a nonmetal? Ionic, which means they carry charges. Do we have a defined charge for lead? Nope. Do we have a defined charge for oxygen? What is that charge? -2, which means the lead must be +2. What's the oxidation state? +2. It ends up coming out the same. Did anything happen to lead? No. Okay, so now we'd have to evaluate our sulfur. Okay, and we'd evaluate our oxygen, and we try and process that through. One of the issues that we're going to find with this particular, with this particular example, is that our oxygen changed its oxidation state. Where does oxygen show up in the reactant? One spot. Where does it show up in the product? 2 spots. So if we try to split this into a half reaction, can we do it? Not really. Okay? So that's where this one becomes tricky. Splitting it into half reactions doesn't work. We'd have to use the textbook method. Okay? So how did the textbook go through and evaluate this? We have to look at our reduction in oxidations, but unfortunately we can't split into those half reactions. So what's our oxidation state of our oxygen? Oxidation, which we've been using as blue. So loss of electrons, right? Okay, how many electrons did it lose? 1. What happened in the next set? What happened to our iodine? What's the oxidation state of iodine in silver iodide? How do you know it's -1? Why'd you look at the periodic table?
Because it's ionic.
It's an ionic bond. An ionic bond means you need to know the charge for those species within the ionic bond. Okay? So the oxidation state, or our charge on iodine is -1. What's our oxidation state if our charge is -1? Also -1. What happened to iodine in the course of the reaction? It went from a -1 to -1. Did it change? No. Okay, so it's not a bad idea to guess and say that was what happened, but check it. In this case, we went from -1 to -1. There was no change in our oxidation state. Was it reduced? No. Okay, which means what had to have been reduced? The silver. What was the oxidation state of silver in our reactant? +1. So it's going from a +1 to the oxidation state of silver in our product? 0. What changed? It had to gain an electron. How many electrons did it gain? Gained 1 electron. So what can we go through and do? According to our crossover method, we can put 1s in front of everything. Is our equation balanced? Yeah? Did we have to go through any kind of redox method to balance this? No. Why'd you go through and do a redox method? Because that's what we've been talking about, right? You can go through and balance it before that without actually having to go through and jump immediately into all of that work. How many silver atoms are on the reactant side? Silver on the product. Iodine on the reactant. Iodine on the product. Chromium. 1 and 1. All of our atoms balance out. What's our charge on the reactant side? Charge on the product side? +2. Did we have to worry about balancing that? Why did we bother to go through and do all this electron pushing around? Okay, we don't even have to make sure. We just checked all of that without having to evaluate it. Okay. If we were asked which was oxidized, which was reduced, we now have a valid statement. We went through and did the proper amount of work. Start easy, then work hard. Okay, so balance it first by inspection. Okay, check your atom counts. Do your atom counts balance out? Good. Then check your charge. Does the charge balance out? Good. Now you don't have to worry about doing any other kind of balancing because everything's self-balanced. All the easy stuff was there for you. Okay? Questions about that? Okay. So guaranteed one of these questions will show up on your exam. Okay? As far as balancing goes. Okay? So I would highly recommend you spend the time to get these all figured out. Okay? If you really want to spend the time to go through and memorize it, by all means go ahead and memorize it. There'll probably be 30 to 40 other questions. Go ahead. So on the exam, your exams are largely multiple choice. What would the question be? We've talked about a couple different question types. Could ask for the sum of the coefficients. What's the sum of the coefficients for the one we just solved? Where are your coefficients found? The number in front. What's the number in front of silver or silver iodide? What's the number in front of chromium? Number in front of the next chromium. Number in front of silver. Number in front of iodine. What's the sum of those coefficients? 5. Did I do 5? 1 plus 1 plus 1 plus 1. We get 5. Okay, so that would be the type of question asked. I could also go through, because the larger issue from this section is what was oxidized and reduced, I could ask, which species was oxidized? Okay. Then you would have to go through and evaluate your electron balancings. Okay? Yeah.
If you ask the coefficients in the equation, is there going to be one where the equation's not balanced? Then we have
Yeah.
No, okay.
Yeah.
No,
No, you do have to balance. Yeah, you always have to balance. If I'm asking some of the coefficients, very rarely will you see it where it's already balanced for you. Very, very, very rare. Is there another hand there? Okay. I know the oxidation reduction. Oh, is that a hand? Yes.
we check efficiency for the reactant side and the product side.
Depends on the question asked. If I ask you for the sum of the coefficients, you total them all up. If I ask you for the sum of the coefficients of the reactants, what's your answer?
But check that for make sure the balance of the equation.
Make sure it's balanced before you answer the question. Absolutely.
What's the purpose of total of the coefficiency for? Because
So what if those numbers had changed? The idea is, can you answer a question about it? That's the purpose. Okay? If you didn't balance this properly, would you get 5? No. So you would get the answer wrong, which then proved that you didn't know how to balance. Okay? That's the purpose of asking the question. Okay? But putting it in a multiple choice format that is easy to ask. That's all it is. Okay? We can talk more about that after class. Okay? So we'll go, yeah?
That was a decomposition because the silver iodide.
I would argue that yeah, that one's a bit of an odd format. I wouldn't ask you to go through and define that reaction. It's kind of odd to refer to it as a decomposition. You are breaking apart the silver iodide. So that on its own was decomposing, but you're definitely seeing some other chemistry happening in there as well. Okay. So we'll go back and finish off chapter 7. We've got 2 extra reactions left. What are those extra reactions? Anybody know? Double replacement and neutralization are our last 2 reactions. Okay? We'll come back to the neutralization a lot towards the end of the semester when we actually start to come up with some definitions for individual species. At this point, what we'll do is just look at balancing those. Okay, so we've got some double replacement reactions. You'll be getting a lot of practice with this in your lab this week as well. So, yeah?
It's from last week. So when it's oxidized, is that the reactant or the oxidant?
So if we go there, let me just pull up a new slide here. Maybe it's going to listen to me.
You switch it or you keep
So if we have oxidation, if it was oxidized, what happened?
it lost.
Loss or less loss of electrons. If it was reduced, it gained electrons. Yeah, I know you know that. Doesn't mean I can't ask you. Okay. But what your question now is, what about the agents? Okay. If I have an oxidizing agent, okay, think of it as a spy. That agent is causing something else to be oxidized. If something else is oxidized, what did that agent have to do? It had to be reduced. So the species that is reduced is our oxidizing agent. Okay. I always remember it as agent from what I've been hearing from a bunch of people in here. Apparently we're pushing that kind of lazyism to the extreme. We don't like adding the ing and agent, so we push it to oxidant. Right, my own fault. I keep telling you to be lazy and write everything down. Okay? So that would be an oxidant. If we looked at our reducing agent, the reducing agent caused something else to be reduced. So what happened to it? It lost electrons, or it was oxidized. Okay? So be careful with the difference between those and apply those as carefully as you can, and you should be okay. Okay? Ultimately, those are just definition questions. You're just applying it to a new state or a new question. Okay? Does that answer your question? Okay. So, let's take a look at a couple double replacements. Again, we're going to go through and try and convert our words into an equation. Aqueous barium chloride. To start with, what are we going to go with? Okay, the only thing that we really need to see is those first three words. Barium has what symbol? Chloride. What is the aqueous? AQ. I need a little bit more space there. Before we step any further along, we need to make sure that the formula we've written actually makes sense. What is the charge on our barium? How do you know it's +2? It's in our second column. What's the charge on chloride? How do you know it's -1? It's in that seventh column. Okay? Are our charges balanced? No. What do we need to do? We need 2 chlorides. Okay? This is straight out of chapter 6. We have to apply those nomenclature rules and make sure that each of our formulas is appropriate. It then says reacts with. What does that mean? Plus. It's okay. Simple mistake. Now we can ignore everything else and look at the last 3 words. Aqueous, potassium, chromate. So, where do you guys want to start? K for potassium. Symbol for chromate. Close. CrO4. Okay. Now what do? We still know it's aqueous. The aqueous. What we need to do is make sure our formula balances. Okay? So what we would have to go through and do is check our charges. What is our charge on potassium? How do you know it's +1? First column. What's their charge on chromate? How do you know it's -2? It's one of the ones that you'd have to have memorized. Wow, you guys are in chorus over there.
You have to memorize chromate?
It's not one of the ones I've told you to memorize, but it's one that you would have to look up. Okay? So take advantage of that polyatomic ion sheet in front of you and look at it.
You would give it to us.
Okay? And I would tell you on the test that you would have chromate. Okay? Is our charge balanced? No. What do we need to do to balance it? We need 2 potassiums. Why do I not put a 2 out in front? It's changing the amount of everything after it. The only thing we want to adjust is the potassium, which means we have to put that number as a subscript. okay, immediately after our potassium ion. Okay? Do we need parentheses around the chromate? Not in this case. Really, the only reason we use parentheses, if we go back up to here, we were using that parentheses ultimately to separate out that that 2 was not part of the 3. Okay? Or if we switched it up to, let's pull another one. Actually, I got space up top. Let's go ahead and do it up there. If I did barium hydroxide, so barium and hydroxide, okay, does our charge balance? No, so I need 2 hydroxides. I could put a 2 here. What does that 2 apply to? Only the thing in front of it. The only thing in front of it is hydrogen. We would need the parentheses then as well. Okay? So our parentheses are not a requirement. They're ultimately a clarification tool. They allow us to make sure that that subscript is applying directly to what we want it to apply to.
If they were in there and didn't need to be, would we be deducted for that?
No, I won't take off points for that. Okay? We now have to go through and do the reaction. It's a good thing I left lots and lots of space to do this. Well, shucks, I'll just have to write it smaller. So we had our barium chloride, which was aqueous, plus our potassium chromate. We're saying reacts with, and ultimately to produce now, which the to produce gives us our reaction arrow. Okay? This one you are fully expected to be able to predict your products. So what happens? We're going to switch our ions. So our barium will exchange places with the potassium. So our barium is now going to be bound, or sorry, our potassium is now going to be bound to chloride. What's our formula for chloride? Cl. What about the 2? Why did we use the 2 in our barium chloride to begin with? To balance charge. Do we need that 2 in potassium chloride? No, why not? Because our charge is already balanced.
Why did you do the potassium chloride first?
Does it matter which species we do first? Good question.
Well, it says A, D, so wouldn't that be barium?
What's 1 plus 2? 3. What's 2 plus 1? Get the exact same answer. It doesn't matter which one we put in front. That just happened to be how I saw it first. Okay? Next part of this. Plus. Barium, our formula for barium is just Ba. Our formula for chromate? CrO4. Check our charges. Charge on barium, plus 2. Chromate, minus 2. Our charge is balanced. Yes. Okay? Now what we can go through and do is balance our reaction. Okay? So we can go back through and just like we've been doing in all those other cases, check each of the atoms. Okay? If we start with barium, how many bariums do we have? 1 and 1. Is barium balanced? Chloride, how many chlorides do we have? Whoops. That should be a 2. And we have, how do we fix that? Why do we put it in front and not as a subscript? The subscript changes the formula. Once we have our formula balanced, we cannot change the formula. It must go out in front, which means we now have 2 chlorines. Okay? Next atom, potassium. How many potassiums do we have? How many potassiums do we have in the product? Oh, that was nice. How many chromates do we have in the reactant? How many chromates in the product? 1. What do we do now? Check your work. Bariums. 1 and chlorines. 2 and 2. Potassium. 2 and 2. Chromate. 1 and 1. Now that our equation's balanced, we could say, yippee, we're done. There's one extra issue with this. What is missing from our equation? Our phases. This is one of the big things that's going to be different about these reactions or double replacement reactions over the other ones. You're expected to be able to predict the phase. How do we predict the phase? Since you've all done the homework, how do you predict the phase? There are solubility rules. You have to know the solubility rules to be able to predict whether our phases are appropriate or not. Okay? We'll talk about that in a second too. Okay? We'll go ahead and skip that next one because we'll see that again in a second here. So with our double replacement reactions, what we're looking at is exchanging our ions completely, and in the next step of it, we need to be able to predict the phases of those products. And that's a pretty big jump to be able to do. To do that, we have to have, okay, apparently I gave you the answers. To get those phase informations, how do we know that? We have to have some understanding of solubility rules. Okay? So there's this big list of solubility rules for you to go through and apply. Okay? When it comes to the final, I'm going to have to check on what information is actually supplied as far as those rules go, and it sounds like we will probably have most of that information. I would recommend, even though that information is supplied, you should spend some time to memorize a little bit of this. What's that little bit? All of it is a lot of it. I would pick, whoops, the first three. Why the first three? If you take a look at all the other rules, what do all the other rules have? Very clear exceptions. Those first three, how many exceptions do they list? None. Which means if you see one of those ions, what's going to happen? It's soluble. What does soluble mean? It dissolves in water, which means the phase is aqueous. We write the AQ after it. Okay? If you've got those first three memorized, you can at least eliminate some of your answer choices. Okay? So let's go through and take a look at that first problem that we went through and evaluated. Now that I've unbalanced it, that was nice of me. Okay, what are our phases? So what's the phase for potassium chloride? How do you know it's aqueous? Rule number 1 says our alkali metals, lithium, sodium, potassium, soluble. What does that mean? Dissolves in water. What happens with our barium chromate? Now it becomes a little bit trickier. It's not one of our rules to memorize. Okay? We'd have to go through and find chromate on our list. Where's chromate? Rule 7. Okay? So rule 1 are our exceptions, which means anything with chromate is insoluble, which means it's a solid. What's our phase for barium chromate? Solid. Okay? You will find, depending on where you look for your solubility rules, that there are tons of different options out there. Okay? And we can almost always find an exception to these. So what ones are you going to be expected to be able to predict and use? The ones that follow off of the chart that you're given in your textbook. Okay? You will need this chart when you're trying to solve all of these problems. Remember, some of this information will be given to you. If it's not, it's going to fall under those Rule 1, 2, and 3 applications. Okay? What happens in the case of this reaction then? We form a solid, which means chemical or physical change? Chemical change. We have a change in phase without a change in temperature, or without a supplied change in temperature, which means we have a chemical reaction. A reaction occurs. What happens in the other case? When we looked at sodium chloride being mixed with lithium nitrate. If I go through and draw this out real quickly, we would expect sodium nitrate as one of our double replacements and lithium chloride. Are our formulas balanced? Yes. Is our reaction balanced? Yes. How many of you could see those yeses that quickly? Ooh, that was feisty. Yes. No, that's cool. You should be able to see it that quickly. Okay. Now we'd have to specify our phases. What's our phase for sodium nitrate? How do you know it's aqueous? Rule 1 and 3 both specify that that's going to be aqueous. How about lithium chloride? Aqueous according to Rule 1. We took 2 liquid or aqueous solutions, we mixed them together, and we now have an aqueous solution. Did we do a reaction? No. No chemical reaction, which means, just like with the single replacements, instead of writing out and balancing with all of our reactants and products, we could just as easily have written no reaction. Okay? To be able to predict that no reaction, for me personally, I want to be able to see what those possible products could be. So I will always do the double replacement reaction so that I can see it and then evaluate after the fact. Okay?
So those three will always be aqueous?
As far as you're concerned, yes. Not solid. So yeah. What we're looking at is soluble, which means dissolves in water. Insoluble, which means did not dissolve in water. If it didn't dissolve in water, we're looking, as far as we're concerned, solids. Okay. There are other things that show up. You could see gases and liquids. Won't see those in the double replacements that I can think of. You'll see those as decomposition reactions. Okay.
You don't have to be able to.
Which you won't be expected to predict. All right, let's take a look at one more. So, double replacement, what happens? Lead swaps with potassium. So we end up with lead being bound to iodine. Okay? Our other possible one would be potassium bound with nitrate. Okay? Before we go through to balance the equation or even predict if we have or predict our phases, we need to make sure our formulas are balanced. So, what's the charge on potassium? Charge on nitrate. Does our charge balance? Yes. Charge on iodide. -1. Charge on lead. Don't specifically know this, at least based on just the information given with our lead iodide. What are you referring to? What did you say the charge was? Lead's in a gray area. It's going to have to be something we're going to specify. Go back to our reactants. What's the charge on lead in our reactant? +2. Okay. In our double replacement reactions, what's going to happen with our electron charge, our electric balance? Will stay the same. We would expect our lead to come out as what charge? +2. Stays the same. Is our formula balanced? What do we have to do? We need the subscript after our iodine to balance out our charge. We now have our lead iodide. Is our equation balanced? Nope. What's wrong with our equation? Okay. We don't have it quite balanced yet. We can go through and put 2's in these cases, and we should have that balance out. Check our phases. Okay. Potassium nitrate. What do we expect? Should be aqueous. Why should it be aqueous? Go through and use your rules. We're looking at potassium and nitrate. Both of those fall under those memorization of aqueous. What happens with our lead iodide? We'd have to find our iodide ion, which is going to fall under Rule 4. Halide ions, in general, are soluble with certain exceptions. What are those exceptions? Silver, mercury, and lead. So if the exception to our rule of solubility is, or if we have an exception to solubility, that means lead iodide is solid. Okay? Flip your reactions, use the rules to predict your phases, and you should be set to go. Questions on that? Okay. Last reaction that we would look at, we're done at 30, right? 40? 40. Oh, good. Neutralization reactions. Okay. We will come back and reevaluate these towards the end. what we're looking at here is a reaction between an acid and a base. Arguably the most important chemistry that you will see throughout the rest of your lives. Okay? Even in organic chemistry, we go through and try and specify our acids and bases. Why? If I have an acid, what is it going to react with? A base. If I have a base, what is it going to react with? An acid. So if I can identify that I have an acid, that means I need to react it with a base. And I can start to push those individual reactions along. We will get variations in the overall products. As far as you're concerned right now, our neutralization reactions are going to have very characteristic species. We'll be looking at our acid with the general formula with an H in front, which we've learned already from our acid nomenclature, reacting with our base. Okay? In the process of that reaction, our A and B, so our anion and our cation from our base, will combine to form a salt, also known as an ionic compound, and water. Okay? So you're looking for that overall relationship with each of your acid-base reactions. Product of the complete neutralization of sulfuric acid with potassium hydroxide. And I'll be nice and add an extra little information here with, that says aqueous potassium hydroxide. So to start off with, where do you want to start? Hydrogen's a good place to start. We're starting with an acid. So we're looking at our sulfuric acid. Notice this is a pretty weak spot with a lot of the quizzes. How do we convert that into a name or a formula, sorry? We know there's hydrogen because it says acid, which also means for us, with aqueous, what's the rest of it? And A doesn't count. We're looking at the sulfate anion. So go back to your nomenclature rules and check and verify that that is indeed what you need to have. Is our formula balanced? Charge on sulfate? -2, charge on hydrogen. +1, our charge does not balance. What do we need to do? 2 hydrogens. Plus potassium hydroxide. What do we do there? KOH. Charge on potassium. Charge on hydroxide. Balanced? Yep. Goes to our products. What are our products?
H2OH.
We have HOH and our SO4 needs to be bound to potassium. Check our formulas. It's the charge on potassium. +1, charge on sulfate. -2 is our charge balance. No, what do we need? 2 potassiums. Do we need to check our formula for water? HOH? No, we don't have to check that. Hopefully we know that water is indeed H2O. Okay.
I'm sure you've talked about this, but what reason is it that you write it out as HOH instead of H2O?
We're about to talk about that in just a little bit. We could then go through and specify our phases. When it comes to our neutralization reactions, water will always come out as a liquid, and we're generating a salt, which most salts are aqueous or water soluble. Okay. Is our reaction balanced? Should be a big no to that. Now it should be balanced. So the more important question here, we've got 2 big ones. Why did we write it out as HOH? And then someone floated out somewhere over here, did this look like a double replacement reaction? Is it a double replacement reaction? We took the front species and we put it with the new anion. We took that one and we put it with a new cation. Our neutralization reaction is a double replacement. If we write it out as H2O, it's not as obvious. If we write it out as HOH, We can see where those species individually came from. It helps accent the fact that we're looking at a double replacement. Our neutralization reactions are just a special case of double replacement. That special case is that we are looking, heads up. We are looking at an acid being mixed with a base. Yes.
Are we always going to generate water?
You will always generate water. For this class, yes. Okay. I don't remember what your textbook throws at you. They might throw something a little bit different than that. I tried to pick questions that were only generating water. Okay. Questions about your neutralizations? Questions about anything that we've covered? I did just write the quiz, so I should remember questions or answers right now. All right, so we'll do quiz in the last 5 minutes. When you're finished, you're more than welcome to turn it in and take off, because there's only 5 minutes. And we will continue on Thursday, looking at the concept of a mole. So everything we've done so far has been pretty in general.